Okay, so we're going to do a second day of Riemann sums, and I just really wanted to kind of recap what we did yesterday because it kind of falls in line with what you hopefully did last night for your homework. So remember that when you're doing Riemann sums, you're given this table, okay, and you can make a graph. Eventually we want to be able to do this without having to make a graph every time, okay? Most important thing moving forward is you have to determine what your subintervals are, okay? They're either going to tell you or they're going to tell you how many that you have, and you have to determine that 4. In the gorilla problem, it was 0.5, and in this car problem, it was 4. Now, as far as what the height of the rectangle is, that determines on whether they tell you left, midpoint, or right. And so we did all this yesterday, okay? This was all on page 2. And then on page 3, we started the trapezoid. Oh, we actually did finish it, I guess, yesterday. So we reviewed how to find area of a trapezoid, and we found area of the trapezoid. Okay, it's just by averaging the two faces, basically averaging the left and the right, and multiplying it by your subinterval. And we got 404 feet. All right, now, which of our answers was an under approximation? Now, your choices here are left, right, midpoint, or trapezoid. Left. Why? It was the smallest one, and we were always picking the smaller number. Now, in this case, left is an under approximation. That's not always the case. It only happened here because my speed was increasing. If the speed had been decreasing, I would have a different result. Okay, what'd you guys get for which one was an over approximation? The right. And again, it's not that the right Riemann sum is always over, it just was in this problem. Okay, and then you were supposed to calculate average to parts A and B. And so this was averaging those two numbers, 284 and 524. And we are on page 3, if any of you are trying to find where we're at. And what did you guys get for this average?
134.
We should have got 404. If you didn't, just double check your calculation, which is the exact same thing we got for trapezoid. Now that's not a coincidence, okay? Think about how we did trapezoid. We were averaging the left and right numbers. So it makes sense that if I have a left Riemann sum, I want you to write this on your notes. A left Riemann sum and plus the right Riemann sum over 2, if you average those two, that is the same as your trapezoid Riemann sum. So in the future, if I've already asked you for the left and the right, and then I ask you to do trapezoid, you don't actually have to do trapezoids. You could just average those two numbers. Or you could use trapezoids. It doesn't really matter, but you have options here. All right, and so this is the most interesting question, I believe. Which answer is the best? Trapezoid? Anybody think midpoint? It could be midpoint. We don't really know exactly. In this particular problem, it's kind of really hard to tell. Impossible to tell with what we know. And so that's that. Ultimately, what really makes our answer the best is increasing the number of rectangles or trapezoids. The more you have, the more accurate your answer is. And I'm going to kind of explain why in a few minutes. Okay, turn to page 4 in your packet. Remember, it was not in order. Sorry about that. It gets towards the back. And so on the questions we did before, we were given a table. Here, what are we given? A function, an equation. We're given a graph that we can use, but we're not given our own table. So we need to come up with a table. So up at the top, I want you to go ahead and write a little x, y, or f of x. And I already kind of mentioned this, but we have to figure out what our subintervals are first. Okay, we're definitely, we know our total interval is 0 to 2. And we know there are 4 equal subintervals. So how long is just one subinterval? 0.5, right? You're going to divide 2 divided by 4. Okay, so think of it this way. This is 0.5, that's 1, and this is 1.5. You have 1, 2, 3, 4 subintervals from 0 to 2. All right, and those are going to be your x values up here. So we're going to start with 0, 0.5, 1, 1.5, and 2. And we're going to have to come up with the y values in the table as well. Just use your function. So if x is 0 squared plus 1, that's 1. So I'm going to put it in the table, and I'm also going to graph that point on this graph. Okay, what about 0.5 squared plus 1? 1.25. I'm going to mark that. What about 1 squared plus 1? 2. Feel free to use your calculator, especially like on this next one. You could do it by hand, but you should get 3.25 and 5. And because this is a function, let's just go ahead and connect the dots and make it into a nice parabola, which is what it is. It's a parabola, parent function shifted up 1. Okay, so we got everything set up. Now we're going to do a left Riemann sum. Okay, so think about it either here or actually drawing the rectangle. What are the dimensions of my rectangle? What's the height? 1. We would pick the left number. The base is your subinterval, 0.5. So 1 times 0.5. That's the area of the first rectangle. That's the first part of this problem. Okay, what about the second rectangle? If we pick the left number, what would that height be? 1.25. So remember, we're going to be adding these up. So we're going to multiply 1.25 by 0.5 again, because that's the base of this rectangle. We're just finding area, base times height of the rectangles. And we just keep going. So you can either use the graph or you could use the table. Thinking about each time with each pair, use the left number. So we're not going to use 5 for the left Riemann sum. And we're going to multiply and add it all up. And I encourage you to do this along with me. Make sure that you're comfortable with typing it in the calculator. And as you do these problems, I want you to think, like, how would you do this if you weren't given a graph? If your answer to that is freak out, then you're going to have to draw a graph every single problem that you do, which is okay. But I want you to make the connection to the table. Like, how do we get these numbers off the table? All right, so was this an over or an under approximation? And so this is what I want you to consider. The true answer, I'm going to do this in blue. The true answer is this outline shape. Everything under the curve between 0 and 2 all the way down to the x-axis. So are my red rectangles over or under this shape in blue? Under. We can see that physically. We have to put an explanation, and that is because f of x is increasing. If f of x had not been increasing, this would not have happened. I'd have a different result. you don't have to prove that f of x is increasing, but if we did, how would you show that you know that f of x is increasing? What do we do in December? What's positive?
Velocity.
Okay, so if f is increasing, then f prime would be positive. What is f prime? So in this case, f prime would be 2x. For these particular x values, 2x would be positive always. So that's kind of a way you could do it. We're not going to take it that far, but I'm just putting it out there. All right. A right Riemann sum. Still n equals 4, so everything's going to stay the same. And in fact, I'm going to use the same picture. So remember, instead of using the left, you're going to use the right. And so I can already tell that this is going to give me bigger values. We could use the graph. I could be using the table. I want you to make the connections between the graph and the table. I also want you to see that once you do the left, the right really isn't that different. It's kind of like you skip the first one, and the second one now becomes the first one. And then we are going to use the 5. And then multiply and add all that up. And we already said this was an over. Our justification is the same. So I'm going to let everybody get caught up here. Check your answer, 5.75. Okay. Hopefully you're feeling a little bit more comfortable with this whole Riemann sum stuff. All right. Part C says to do a trapezoidal Riemann sum with the same amount of n equals 4 equal subintervals. So what do you guys think? Could I find the answer easily? Yeah. Let's average the answer to part A and part B. You could maybe average these in your head just because of these numbers, but you get 4.75. Now, I do want to go ahead and graph this and analyze it a little bit further, especially to answer the second part. But I want you to see that's how easy it would be to come up with the answer. You didn't really even have to draw the picture. I am going to draw the picture, though, for the next part. I got shaky hand today. That's good enough. Okay, just as a reminder, before I get into the whole over-under thing, I could have done this by just connecting the first point to the second point and actually drawn a trapezoid. And so that would have meant averaging the 1 and the 1.25. And then still times 0.5. So I could have done it that way. You might want to put that in your notes if you feel like you need to. We've only done one trapezoid example, so I wanted you to at least have another one in there. If we had not had parts A and B, you could have done them, even though you didn't have to, and then averaged, or you could have just done trapezoid. I just want you to be comfortable either way. All right, now here's the next question. So remember that the area under the curve is going to be represented by all this blue stuff, okay? I'm going to use this last one. If I connect these 2 points and make a trapezoid, I want to know, is the trapezoid going to be bigger or smaller than this curve? It all depends upon how this curve is bent here. So what do you think? If I connect these 2 points, should this straight line go above or below this curvy part of the parabola? Why above?
Because the slope is being concave up, and you just need it to be a linear line.
So how do you know that this is a concave up graph?
Because you can see it.
Because I can see it. How would we know for sure?
Because it's positive.
What's positive?
F of x.
So f of x is x squared plus 1. What's f prime again?
2x.
2x. What's f double prime? 2, which is a positive number. So we could go all the way back to that stuff. But we can see that this is a parabola. It's going to be bent upwards. It's concave up. So if it's bent up, and I can kind of like really exaggerate the concavity here. If that is how the graph looks, the trapezoid is just going to be a straight line. And so in this case, the trapezoid is bigger than the actual area under the curve. So this ends up being an over approximation. And our justification has to do with concavity, because f of x is concave up. Again, you don't have to prove that, although you could if you needed to. You'd have a different result if f of x was concave down, and you'll see one on your homework like that. This is not something you have to memorize. If you just draw an exaggerated picture of the concavity, you can kind of figure it out like how we did. Okay? Any questions on that? All right, let's do midpoint. What's different, besides midpoint, what's different about this one? Sure. N is 2, and this is a really good news, by the way. So let's go ahead and draw our graph.
Wait, I have a question.
Sure.
If you don't have a graph, how do you know that it's concave up?
You'd have to actually either think about the parent function. You'd have to say, if I don't have a graph, is this parent, what do I know about this parent function? I know it's a parabola. I know the coefficient in front is positive, so I know it's concave up. Or actually find the second derivative.
Okay.
It would have to be something that you could easily figure out. I wouldn't give you a really complicated one without also giving you the graph. Okay, so here is our picture again. Now I went ahead and graphed all the points, because even though this is n equals 2, so what this means is, here's my first rectangle. But I need this point in the middle because I'm doing midpoint Riemann sums. So that's going to be the rectangle right there. So the height of this rectangle was the y value right here, which was 1.25. The base, though, is different. What's the base of this rectangle? 1, not 0.5, because there's only going to be 2 rectangles, not 4. So 1.25 times 1 plus, and then you do it again with this one. Oops, whatever. 3.25 times 1. You should get 4.5. Notice it does not ask you if this is an over and under. That's a little bit harder to gauge here. You would have to do a lot more work. We're not going to do that. If this had said n equals 4 still, we would have had to do a lot more work. I would have had to then plug in like 0.25 and 0.75 and made my table bigger. Okay, so that would have been annoying. So we'll just be glad we didn't have to do that. All right. I want to show you something. And here's a computer applet, and this is, I've already put in, this is what we just did. So which out of A, B, C, D, which one is this? Yeah, this was the left Riemann sum. This was A. Okay, so, and we can see this is the answer we got for A, 3.75. Left sum, we can see this, n equals 4 rectangles, and I went ahead and put in x squared plus 1 to be the function. Now, if I slide this little thing over to the right, I can see that's the answer we got for part B, 5.75. All right, and if I slide it to the middle, then we get this. This is not the answer we got for part D. Why not?
Because they used
This is using n equals 4 rectangles, but we only used, 2. And so 4.5, that is the answer we got. All right, this one does not do trapezoid, this particular applet doesn't, but it does find the actual area. So I'm going to click that on and click the rectangles off. And this is the true area that we kind of have been talking about, but we haven't known yet. All right, and so this has calculated that. So we can kind of see that our answers were pretty close. Midpoint and trapezoid were pretty close to the true answer. Okay, what could I do here to make my Riemann sum closer to the actual area? What could I do here? Yeah, make more rectangles. Oops, I should probably show it. There we go. So we started back over here. If you make more and more rectangles, you can see both in the numbers and in the graph that adding up the area of the rectangles is getting closer and closer to the area of that weird curved shape. Okay, so this is using technology to figure out that actual area. All right, and your graphing calculator will do this as well. Very soon, your brain will do this as well, but not today. Aren't you sad? No. All right, so I want you to turn to page 5 in your packet. And at the top it should say the exact value for number 2 is represented. And then we see this. We have not seen this yet. Okay, so just let it soak in. Okay, it's no big deal. X squared plus 1, that's just the function. Dx, that just means with respect to x. Okay. 0 to 2, where are those numbers coming from? Yeah, the interval, the starting and stopping point. All right, so that's what that means. This just means adding up the area under the curve. This is the first time you're seeing it like this. You'll see it a lot more, just getting you used to it, okay? So this is how your calculator will do this. So first of all, you want to go to the F3 menu on your calculator. So turn your calculator on. And if you wanted to, you could do F1, you could clear, so F1H. That'll clear that. Remember, you can clear your variables by doing second F1. You may or may not want to do that. And if you see F3 calc, we go F3 calc, and the choice number 1 is differentiate. This is how we got our calculator to take the derivative. Well, choice 2, now we're going to put a name to this, integrate. So choice 2, integrate. That's what we're doing now. And I haven't even explained what that means. But go ahead and write this down on your notes, and if you would like, put this on your TI-89 foldable that we started at the beginning of the year. That was just there to help you remember all the calculator steps. This is what could go on the very last page. And so when you do that, it opens up. It uses kind of that same notation. I'm not even really explaining what that means yet. And then we're going to type in the function. So x squared plus 1. If you're thinking, where's the 0 and 2 going to go? I'll show you in just a minute. But first we're just going to type in the function. And then what have we always been doing every time we type something in? Comma x. So we're going to do that again. So comma x. And now we're going to do comma 0. So the lower number, comma. Oh, I did forget the squared. Thank you. Thank you very much. All right, and then comma 2. and then close your parentheses. So you put in the function, comma x, comma lower number, comma upper number. And this is not, we don't know how many subintervals there are because this is like acting like there's a whole bunch. It's going to give us a really accurate answer. Now, if I press enter right now, it's probably going to give me a fraction answer. And it does. And you can see here that it puts it back in pretty print, and this looks more like what was typed on the paper. If we want it to give us a decimal answer, which is helpful here just to compare, we would do diamond enter. All right, and we get this 4.666, which is what we saw on the computer applet, and it was really close to the answers we got by doing Riemann sums. Okay, so I'm going to write all this down right here. Okay, so that was your first kind of exposure at this notation. No big deal. It's just adding up the area under the curve, and now we know our calculator can do that. This only works if we have the equation, by the way. This doesn't work on the table problems. Okay, so trapezoid and midpoint were both pretty close. But we know the key to really getting an accurate answer is to have lots and lots of rectangles. Okay, so let's move on to our last example for today. And that is, in order to determine the average temperature for a day, a meteorologist decides to record the temperature at 8 times during the day as indicated by the data in the table. Use a Riemann sum with the intervals indicated in the table to estimate the average temperature during the day. So what we're trying to do is find average temperature. Now, if someone just walked in here, like someone else, like an office aide or somebody, and they said, oh, you're trying to find average temperature, you just need to take these numbers, add them up, and divide by however many there are, which would be 8, right? Am I counting that right? So why would that not give us the best answer?
Because isn't the average is the same as time intervals?
Yeah. I'm sorry, I didn't mean to be like that. Yes, but there's also another reason. So keep guessing.
Do they overlap? No.
They don't overlap, but look at how they're not evenly distributed. This 42 degrees is for 5 hours, whereas 57 is only for 2 hours. Have you ever heard of like weighted averages? Mm-hmm. It's kind of like why you can't just average a homework grade of 100 with your test grade of 80 to get your 6 weeks average. So this is where we have to do a little bit more work here. Now this says to use a Riemann sum. Now I think some of you could probably figure out how to answer this without even knowing what a Riemann sum is. But let's go ahead and use the strategy here. So 42 would be what we want to use. 42, that's the height of the rectangle. And I'm not even graphing this, but if I did, that would be the height. Okay, how many hours for 42? 5. Okay, what about 57? 2 hours. Okay, so you got the hang of it, so go ahead and I'll write it down and you write it down. Okay, so we're going to be using the calculator a lot in this chapter, so if you didn't bring yours today, please make sure that you're bringing it to class, because this is kind of annoying to do on your phone. And you're not going to get to use your phone on the quiz on Friday anyway. So I got 1584. So my answer to the average temperature during the day was 1,584 degrees. What do you think about that?
That's hot.
That's pretty hot.
Maybe it's in Celsius.
Maybe. That'd still be hot.
Like
So did I really calculate average temperature, or do I have another step?
We still have another step.
I have another step. What do I need to do?
Divide by 8.
Divide by, so 8 or 24? What was the total amount of time? 24. So I'm going to put a little 1 over 24 here. You got to divide by 24. You got to divide by your total time. And since we started at 12 a.m., ended at 12 a.m., that is 24-hour period. Okay, and I get 66 degrees, which does seem like the right answer. All right. How are you going to know when to divide and when not to? Well, just reasonableness of your answer is one way, but also they asked us something different than what they were asking us before. They asked us to find the average. When else in this class have you been asked to find average something? Average rate of change. And how did you find the average rate of change? What was A rock like? Slope, okay? And I didn't do anything that looked like slope here. But that's because I'm not doing average rate of change. If they had asked us to do average rate of change of temperature, find the rate at which the temperature is changing on average, that would have been something we could have done last semester. But they're asking us to average exactly what we have, not its rate of change. That's how you're going to know. And this is going to take some practice, and we're going to kind of look at this different ways in the next day or two. But that's how you're going to know. This has a name, and it is called average value. Just like how we have average rate of change, this is called average value. Now in this problem, if I go back to that notation of using the integral, I would do 1 over 24, and I would integrate from 0 to 24 of my temperature. So I could maybe call this T of x dx. I don't want to get too technical here, but I want you to kind of start getting used to seeing this notation. All that means is the area under the curve divided by 24 at the end. Okay? The real formula looks like this. 1 over b, 0 to b, f of x dx. So you don't have to know this formula to do tonight's homework or anything like that. We already were able to come up with the answer otherwise. But I want you to make some connections between this and where we go with this next. Okay, I want you to turn to page 6. And it has Riemann Sum's homework at the top, if that helps you. Okay. You are going to do page 6 right now before you leave. You're going to finish page 6 before you leave. You got plenty of time. Okay, it's just kind of one problem, a few different parts. There's some misspellings, by the way. See if you can catch them all. And then 7, 8, and 9. This is your homework. You don't have to have all of this done by the time you walk in tomorrow, but you should definitely have page 6 done and some of the other stuff done. We have a quiz Friday. That's like the day after tomorrow. So tomorrow, if you haven't had any of this done, you might feel already behind. So tomorrow, you should definitely have page 6 done, some of the other stuff done. We'll continue all this tomorrow, okay? And then quiz Friday. Over